Hello, I'm Lucy, and this video is about enantiomers. What is an enantiomer? An enantiomer is a molecule in a pair of molecules that have the same chemical components but opposite geometry. These two molecules exhibit mirrored symmetry. First, we'll discuss some vocabulary. Most importantly is the term chirality. An enantiomer is a chiral molecule, as chirality refers to mirror asymmetry. The word chiral is derived from the Greek word for hands, and hands make a good analogy for molecular chirality. Each hand has the same amount and type of fingers, one thumb, one pinky, etc., and all of your fingers are connected to your palm in an orderly manner, but your left hand and your right hand are not superimposable. They are mirrored. R and S are prefixes that distinguish enantiomers from each other. R molecules have clockwise geometry, and S molecules have counterclockwise geometry. To discuss chirality, we will use clay to represent atoms. Blue clay is hydrogen, white clay is carbon, red clay is oxygen, purple clay is chlorine, and the green clay broccoli is a butyl group. The first molecule we will examine in our quest to find chirality has two hydrogens, an oxygen, and one carbon atom attached to a central carbon. It is important to note that the side carbon needs 3 more bonds to be stable, but while looking for chirality, examining the atoms directly bonded to the potential chiral center is sufficient. We will call this molecule A. To look for chirality, we will switch 2 atoms and compare the new molecule to the old one. Here, we will switch the oxygen with the hydrogen to form molecule B. Now, we are going to rotate our new molecule to see if it is the same as the original molecule or if it is mirrored. Now we will compare molecule B to molecule A. As we can see, the 2 molecules are identical and superimposable. This molecule is not chiral. Now we will examine a second case. Here is molecule A. This time, our molecule has 4 unique side groups: a hydrogen, an oxygen, a carbon, and a chlorine. Again, we will switch the hydrogen with the oxygen to form molecule B. Now we begin our rotation. Let's compare molecule B with molecule A. This time, something is different. The carbon and the chlorine groups are in opposite positions. These molecules will never be superimposable, no matter how much we rotate them. We can see that molecules A and B are mirrored, indicating that they are chiral. Molecule A is the R enantiomer, and molecule B is the S enantiomer. To determine the chirality of an enantiomer, we can start by giving our molecule a pat to flatten it. There we have our flattened molecule, with the triangle on the carbon side group to remind us that it was pointing up before we squashed it. We need to look at the atomic number of our side groups to determine the rotational geometry. The highest atomic number receives the highest priority, and the lowest atomic number receives the lowest priority. For clarity, we will label our side groups A through D in order of descending priority. To determine chirality, we make sure that the D group is pointing away from us, as denoted by the dotted line. From there, We will follow the side groups from A to C. For this molecule, priority goes from chlorine to oxygen to carbon in a counterclockwise manner. Our molecule is an S enantiomer. As an example, this is a pair of enantiomers that I use in my research, R and S phenylethylamine. To determine the chirality of a chemical experimentally, the best method is circular dichroism spectroscopy. Chiral molecules have the ability to induce circular polarization in light, so the CD spectrometer passes a beam of light through the sample and measures the rotation of the beam. Chiral molecules have many uses and applications. Many proteins in the human body have chiral centers, and the enantiomers of some chiral drugs can be significantly more toxic than the drug itself. Chirality can even have uses in semiconductor devices. This video is sponsored by Ethanol Dog. Thank you for watching.